Welcome back to ECE 320A. In this video, I want to just remind us that we're in Unit 1, and that means we need to be reading Chapter 10. We need to finish up homework number 1 at the end of Unit 1, and at the end of Unit 2, we will be giving exam number 1. With those announcements, let's examine what we want to do in this video, and that is to start talking about Chapter 10 material, which is the sinusoidal steady-state power, and we're dealing with single phase, or I might abbreviate that as 1 hyphen or 1 dash phi to be single phase power. We'll define the passive sign convention and what that means, or how we need to incorporate that when we're finding or calculating powers. We'll develop the notation for voltage and current that we will be using, and that really is selecting time t equals 0. We have sinusoidal steady-state conditions going for all time. We now want to simply draw a line in the sand and say, where are we placing t equals 0? And we'll place t equals 0 when the current is at its maximum or at its peak value. And we'll see what that means relative to the phase relationships or the definitions of these phase angles on the voltage and current. Once we have that notation, we can start looking at instantaneous power. And from instantaneous power, which is this lowercase p of t, which is now just the product of voltage and current at any given instant of time, little t, then from that we'll determine what the average power P is, and subsequent lectures will talk about the reactive power Q. But I'm giving you those formulas so that you can look at them now. You can either write those in terms of peak values of voltage and current or RMS values of voltage and current, and we'll probably favor writing those in terms of RMS because then we don't have to keep track of that factor of 2 in the denominator. But essentially, one way of looking at this is the average power is the real power. That's what's being used to drive loads, and that's going to be VI cosine of the difference between the voltage and current of that particular load or element, and the reactive power is 90 degrees from that. It's the sine of that angular difference between the voltage and current. Those are some things to just keep in mind, and we'll see where those come from as we walk through the material or work through the material. Let's start then in Chapter 10 with single phase power. Again, it's sinusoidal steady state, and we first need to establish this convention of what we will be basically labeling with a positive sign when we define power. And that's going to be based on what we'll call the passive sign convention. And we may not even make that very clear as we're working through. It will just be intuitive, or we will just assume that that's what we're doing. But here's the definition of the passive sign convention. And I've left one place blank for us to fill in so that if you're following along, you can at least fill in that blank. With the power, or with the passive sign convention, what we are saying is that the power absorbed by that element, here we're just having a 2-terminal element and we're calling it a generic element. That means it could be some combination of R, L's, and C's, or it could just be an R or an L or a C. But we will define, using the passive sign convention, the power absorbed is given by a positive sign when the defined current enters the positive terminal. And here you can see that I of t is going into the positive voltage terminal of this generic element prior to the current flowing through or continuing on through that generic element. Meaning the current is touching the positive polarity. And don't fuss over how you've been given or assigned current and voltage. Just live with what you have. Don't worry about the direction or the polarity. Just use what you're given and go from there. And in that sense, if you see that the current is drawn such that it enters the positive terminal voltage prior to going through the generic element, then that will have a positive value when we multiply V and I times itself, and we'll call that then the passive sign convention, and the power will then be absorbed by that particular generic element. And whether it's actually absorbed in reality or supplied, that will all fall out as we go through the algebra. So here, let's just quickly check our understanding on what we're saying. Here, if this is now our generic element, and we're confronted with a current I going to the right, and we have polarity labeled plus to minus from the top terminal to the bottom terminal, then P of t, defining the power of that element, and we'll be talking about instantaneous power, average power, reactive power, but here it's just the instantaneous power, is now positive V of t times I of t. And if it so turns out that that result ends up negative, then in fact, in reality, that generic element is absorbing a negative power, or it's actually supplying power to the rest of the circuit or rest of the system. Another case. We now have I of t, and here, what's actually happening? Well, if this confuses you, what you could do is you could say, well, I'm used to it, the current being close to the positive polarity labeling of the voltage. Well, you could make that happen by saying, oh, I have current here. That's the same current as you have in blue up above. But now look what happens. That current is actually going through the circuit element before it touches the positive polarity labeling. So in this sense, we would have P of t is equal to minus V of t, I of t absorbed. And that's the labeling or the sign convention that we would use. And if it ends up that with that negative sign and the V and the I taken together ends up being a positive value, or at a particular instant of time it's positive, then we will be saying that that power is absorbed. Or, stated another way, if we have negative power absorbed by an element, that really implies that positive power is supplied by the element. So don't really worry about what results so much. Make the conclusion after you've done the algebra, but before that you need to make sure that you put in the proper sign associated with or being consistent with the way that the circuit element has been labeled. That's the passive sign convention. What we now want to do is talk about notation that we will use for voltages and currents. And here again, we could write those in terms of maximum values or peak values or RMS values. And since they're sinusoidal, those are related by this factor of square root of 2. But you can see now that the cosine has a phase shift of theta sub v plus theta sub v. They're both at the same frequency, omega. And the current, we're saying, has a phase of theta sub I. But this gets a little bit messy when we're combining sines and cosines. So the convention that we will use is we will select our time reference such that we'll draw the line in the sand on these sinusoids where t equals 0 corresponds to the current waveform having its peak at t equals 0. That's where we're selecting t equal to 0 in this infinite expanse of sines and cosines or the sinusoidal waveforms. What does that mean? Well, that now allows us to actually rewrite this voltage and current in a little bit cleaner fashion, meaning we collapse or we put all of the phase or the phase shifts, the angles in the voltage expression. How do we do that? Well, here's a little bit of an aside, and I'm not going to spend a lot of time on this, but you can work that out. Suppose we define a t-bar such that I of t actually peaks at t-bar equal to 0. So we're looking at the argument of our current, and we're saying instead of omega t plus theta sub I, let's just make that omega t-bar. And then that gives us a relationship between t-bar and t. We divide through both sides by omega, and we have t-bar is equal to t plus theta sub I over omega. Or if we solve that for t, then we end up with t is equal to t-bar minus theta sub I over omega. And that says then that we also now have this current expression without a phase shift. What does that do with the voltage waveform? Well, if we rewrite the voltage waveform in terms of t-bar, now we replace little t with t-bar right there in terms of t-bar and theta sub I, and you can now see with the algebra that the voltage is now going to contain all of the phase difference, which is theta sub v minus theta sub I, and the current is going to not have a phase shift in its argument. So now when we're working with voltages and currents, we'll just say the voltage phasor is going to be theta sub v minus theta sub I in these subsequent developments, and the current doesn't have a phase shift. Now that we have that, let's just forget the t bars. Let's just put them all as t's again. And now we're going to say, here's our notation. Our voltage is going to be v sub m cosine omega t plus theta sub v minus theta sub I. And I of t is now equal to I sub m cosine omega t. Again, if we wanted to, we could write that in terms of RMS values. What we want to do now is look at the instantaneous power. Now that we have our notation in place, let's now use that notation to find little p of t, which is just the product of v of t and I of t. And if we keep the amplitudes, the product of those out front, now we have cosine due to the voltage waveform, omega t plus theta sub v minus theta sub I times the current's cosine expression, which is cosine omega t. And it's nice, actually, if we can simplify this or rewrite this in terms of maybe a different set of conditions, or maybe we can separate this out. We now have a product of cosines. If we view this as alpha and this argument as beta, then let's now apply a particular trig identity to the product of cosines and simplify or rewrite that instantaneous power expression. So the trig identity, if you look in the book in Appendix F, this is trig identity number 8, which says that if you're dealing with the product of two cosines, the cosine of alpha times the cosine of beta is now 1/2 cosine of alpha minus beta plus 1/2 cosine of alpha plus beta. And if you wanted to verify that, you can always start relying on Euler's relationships or using the fact that the cosine can be written as this linear combination of complex exponentials and verify that particular trig identity. And that's one way to start gaining more comfort with Euler and sines and cosines, but now when we have exponentials, those are a little bit cleaner when we start multiplying those together versus sines and cosines. But now that we have this way of expressing a product of cosines, let's incorporate that into our instantaneous power formula, and you can see that we're going to have then cosine of alpha minus beta, and that now gets rid of this omega t. The omega t's cancel, and we're left then with two terms, and let's just write those down. The instantaneous power expression now becomes 1/2 V max I max cosine, and the omega t's cancel, and we're left with theta sub v minus theta sub I. That's the first piece. And the second piece, again, is a 1/2 V max I max, but it's now the sum of those arguments of the cosines, and we had omega t and omega t in there twice, so we have 2 omega sub t plus theta sub v minus theta sub I. And now what we want to do is notice what's happened. If we look at what this is doing, theta sub v and minus theta sub I, those are fixed angles or constant angles. That first term that I've now highlighted or underlined in red is just a constant. That's just some number. And this second expression that makes up the instantaneous power, this is actually time varying because of the argument of the cosine, and it's now twice the frequency of our original waveforms of voltage and current. Now what I want to do is apply another trig identity. And the other trig identity, now let me call this piece alpha 1, and this piece of the argument of the cosine beta 1, and the time varying piece of the instantaneous power of a generic element that had a particular voltage and current expression associated with it. And now let's look at what happens when we apply trig identity number 2 to this, which is the cosine of the sum of two angles, alpha 1 plus beta 1. That's now cosine alpha 1 cosine beta 1 minus sine alpha 1 sine beta 1. That's now a second aside, and we will now be able to split that second piece into a couple more terms so that we now have a instantaneous power expression made up of three pieces. The first two, and then we split the second of those two pieces into two pieces, so we result or end up with three separate parts to this instantaneous power. The first one is 1/2 V max I max cosine theta sub v minus theta sub I. That's the constant piece. The other piece is now plus 1/2 V max I max cosine of theta sub v minus theta sub I cosine of 2 omega t. Again, that's using the alpha 1 and beta 1 relationship minus 1/2 V max I max. Again, we're just applying this trig identity, sine theta sub v minus theta sub I sine of 2 omega t. And we're now going to use this formula a lot, so don't dismiss this expression, we won't use it that much, but we'll use it to derive some relationships for the average power of our different circuit elements, resistors, inductors, and capacitors. So that's sort of telling us where we're going with this. For now, let's look at the average power of that particular generic element that, again, had associated with it a voltage V of t and a current I of t, where the two differed in phase by this difference, theta sub v minus theta sub I. They're both oscillating at the same frequency, omega, radians per second. If we now look at the average power of this generic device, or what we will also call the real power, the average, P average, and a lot of times we'll just forget the subscript average, but now we're averaging this over one sinusoidal period, which we'll just say is capital T. And we're now going from 0 to t of P of t dt. And what happens now when we put this three-termed P of t expression inside that integral, and we're integrating over one period? And the last two terms, look at what happens. Those are now oscillating at twice the frequency, which means that they have two periods of their waveforms between 0 and cap t, which means that we have an equal number of area above and below the 0 value for the last two terms in this instantaneous power equation, or that's really saying that the cosine of 2 omega t and the sine of 2 omega t, those terms in this averaging process actually integrate to 0. Which means that we're left only with this average of a constant. And the average of a constant over a period from 0 to cap t is just that constant. Or the average power now is going to be 1/2 V max I max cosine of theta sub v minus theta sub I. And we will probably, as I hinted before, we will probably not be using the maximum values all the time, and we will probably start removing the subscript average, and we'll just call this P. But now in terms of RMS, Vmax or Vm over 2, and well, let's just split that 2 into two pieces and say we have Vmax over the square root of 2 and Imax over the square root of 2. That's really just V RMS I RMS cosine theta sub V minus theta sub I. And that's our average power of that generic circuit element, two-terminal element. And that's actually what we will call the real power. And this real power is really just a measure of the rate of energy consumption used to transfer from electrical energy to another energy, where that other energy could be electrical, it could be mechanical, but maybe, let's just say maybe another energy, maybe another non-electrical energy. So the real power, this P average, is just a measure of the rate of energy consumption. And that's really what's doing the work in our system, and we need to keep track of that. And that means that that's a very important relationship to keep mind or to take away from this particular video. And that's VRMS IRMS cosine of the angle difference in phase between the voltage phasor and the current phasor.